pose a question: which occurs first, thunder or lightning? If you were to say that lightning occurs first, you would be absolutely wrong. Both thunder and lightning occur at the same time. So, even though both of these events occur at the same time, what we observe is we observe the lightning flash before we hear the clap of the thunder. And the reason for that is light travels incredibly fast, while the speed of sound, even though it's really fast, it is very significantly slower than the speed of light. So sound travels slower through air than light. So we see the flash of the light first, and then we hear the clap of the thunder. And if we count the seconds in the delay between seeing the flash of the lightning and hearing the clap of the thunder, we could more or less roughly estimate the distance to that lightning strike. It turns out it's about 6 seconds per mile. And for many everyday occurrences on Earth, we could say that light travels approximately infinitely fast and travels instantaneously, and for most perspectives on Earth, that's a good enough approximation for everyday life. But this technically isn't true, since it does take a certain amount of time for light to travel from a source where that light is created to an observer or camera that is seeing the light. We never really could see an object as it is in the present. We can only see an object as it was in the past. And aside from some very high precision science experiments, this effect is almost always completely negligible for everyday life. So this effect is known as look-back time, and when we talk about astronomy and cosmology, this effect could become very prominent for objects in the universe. If we were to look at the moon, we would see the moon not as it is right now, but as the moon was a little over 1 second ago. So here's an animation of a light pulse being sent between the Earth and the moon. So if you were to call your friend on the phone, you talk with them, you could ask a question and get an answer immediately. But if you were to talk to an astronaut on the moon, you would have to ask a question. It would take time for that signal to reach the astronaut. The astronaut would respond, and then the astronaut would need to send a signal back to Earth. And there would be a small but noticeable delay between you asking the question, them receiving the question, hearing it, responding, and this travel time would be noticeable. Now, for the sun, this effect is even more prominent. The sun is much further away from the moon, so we see the sun not as it is right now, but as the sun was 8 minutes ago, because it does take light time to travel from the sun to the Earth. So if the sun, for some reason, decided to started blinking in some weird pattern, we would not know until 8 minutes after the blinking started, because we see this, it takes light time to travel from the sun to the Earth. If we look out at Saturn, it depends where Saturn is in its orbit relative to the Earth, but on average, we see Saturn more or less as it was about 80 minutes ago. And if we look at Pluto through a telescope, we see Pluto as it was about 5.5 hours ago. As we go outside our solar system, this effect is going to become even more prominent. Rigel Kent, also known as Alpha Centauri, the nearest star to us, it's part of a triple star system. This star we see as it was 4.3 years ago. The North Star is a couple hundred light years away, so we see the North Star as it was a few hundred years ago. Now, there are not very good constraints on the distance to the North Star for various reasons, but it's a few hundred light years away, so we see the North Star as it was a few hundred years in the past. If we go look out at other galaxies, we have the Large Magellanic Cloud down here and the Small Magellanic Cloud up here. These galaxies are really far away, so we see them as they were a little over 100,000 years ago. And if we look out to some galaxies in the nearby Large Galaxy Cluster, we see these galaxies as they were more or less over 50 million years ago. And this is going to be suggestive of the notion of a cosmological horizon. So a horizon in cosmology is colloquially, you could think of it as any region of the universe that we cannot receive a signal from. So one example of a cosmological horizon is inside a black hole. If we're inside the event horizon of a black hole, we cannot see anything that is going on in there. So anything that occurs inside a black hole is cut off from the rest of the universe. So we would say everything in the black hole is beyond the horizon of what we are able to see. In addition to event horizons of black holes, there are also cosmological horizons. There are other regions of the universe that we cannot observe that are beyond what we know as the observable universe. So here's a section of the universe. As far as we know, the universe might be infinitely large. So I drew Earth near the center of the picture, right around here. Earth is actually a lot smaller than this. So let's imagine that an object here is shining and that object gives off light. That object is pretty far away from us, and that object has given off light. That light has been traveling at the maximum possible speed for the maximum possible amount of time, and just today that light is arriving at Earth. So that light has been traveling for the entire age of the universe at the speed of light, and just today light from that object reached the Earth. Well, let's suppose there's an object here and the story is the same and over here. I could imagine that there are a whole lot of objects that have given off light, and light from objects all around here surrounding us have been traveling for the greatest possible speed for the greatest possible length of time. And there's probably an object out here too, but we would not be able to see that object because even though that object has been giving off light, that light just did not have enough time to reach us yet. So beyond a certain distance, we cannot see anything. And there certainly are going to be more stars and galaxies and black holes out here as well, but light from these objects just hasn't had the time to reach us yet. So this is what is known as the edge of our observable universe. By traveling at the maximum possible speed for the maximum possible amount of time, light from some objects just on the edge of the observable universe are just barely arriving at Earth today. So we have a shell surrounding us, which is known as our cosmological horizon, and this is the extent to which we could see. So this shell is about 46 billion light years from the center to the edge, and the universe is roughly 13.8 billion years old. The reason this shell is bigger in light years than the age of the universe is that the universe has been expanding. So when you account for the expansion history of the universe, an object here is about 46 billion light years away today. Now, if this expansion continues into the future forever, we'll never be able to see some galaxies way out here. The expansion of the background, the expansion of the universe can carry a galaxy here away from us faster than the speed of light. And if that's the case, the light from that object is never going to be able to reach the Earth. The light will move towards the Earth, kind of, but the expansion of the universe is going to be pulling it back because there's a lot of space between here that's expanding. So even though the light is directed towards us, it's continuously being pulled away. You can imagine a person is trying to swim to the east, but the current is pulling them to the west. But the current is pulling them to the west faster. So even though they're trying to swim in one direction, the current is just pulling them the other way. And they're never going to really move any further east than they are today. So if there are other astronomers out here, other aliens doing astronomy, it's possible we'll never be able to meet them because the expansion of the universe is just going to pull them further and further away from us. They have their horizon centered on them. There was a star right here that gave off light. That light from that star has been traveling for the age of the universe. It is just reaching their planet today, so they have a limit to which they could see. So light from us will never reach them, and light from them will never reach us if they are outside of our cosmological horizon. Now, in this case, we have two planets that are within each other's cosmological horizon. This planet here on the right could only see as far as the blue shell. Our planet Earth here on the left only sees as far as the green shell. So we can, in principle, see each other. But would we ever be able to, let's say we look, and we send a signal to them, would the signal ever reach them? The answer to that is no. We would never be able to contact that planet. And the reason for that is, again, due to the fact that the universe is expanding. If we were to send a light signal to the universe today, the expansion of the universe would carry this alien world outside of our horizon before the light signal reaches that distant planet. So we would never actually be able to contact that distant planet and send them a signal, and vice versa. We would only be able to see them as that planet was in the distant past. So we might see their predecessors before the aliens evolved into whoever they are today. So the actual regions of the universe that we could, in principle, travel to. Let's imagine we are traveling nearly at the speed of light, just barely below it, are actually much smaller than the size of the observable universe that we're able to see. Now, distant objects are allowed to recede away from us faster than the speed of light because these distant objects are just being carried along for the ride with the expansion of the universe. So if the universe is infinitely large, we could look at the Hubble rule. H0 is just a constant that describes the expansion rate of the universe. So if D becomes really, really large, times multiply D by a constant, you will have a really, really large speed. And there's no limit to how large the speed can be. So a really far away object can move away from us faster than the speed of light because that object is not actively trying to move faster than light. It's just riding along the expansion of the universe. So what are some consequences of an infinitely large universe? Well, in a finite volume of space, such as within our observable universe, there are a finite number of particles, all the particles in the observable universe. Now, these are really large numbers, but the important point is this is a non-infinite number of particles in the universe. So we are dealing with some large numbers. If the universe is infinitely large, you would expect eventually every possible combination of particles should be repeated an infinite number of times. Just pick a random combination or a random arrangement of particles. If the universe is infinite, you will encounter that same arrangement of particles again. Now, I am a certain arrangement of particles. I'm a large number of particles, but I am still a certain number of particles arranged in a certain way. And so I could expect that more or less this number, so 10 raised to the 10 to the 28 meters away, there should be an arrangement of particles that is exactly an identical copy of me. So in other words, the exact same arrangement of every atom and every particle in my body will be repeated more or less at this distance. Now, this is just a statistical approximation, but this gives us an idea of how far away we would need to travel before you meet an identical copy of you. Now, in a bigger arrangement of particles might be the Earth, the Sun, everybody on the Earth, the nearby stars. So if we look at everything within 100 light years of the solar system, that is a large number of particles, but that's still a finite size arrangement of particles. And we expect roughly at this distance, we should find a sphere of radius 100 light years that is identical to a copy of our solar system. And our observable universe, it's huge, but still a finite number of particles in a certain arrangement. And we expect about this distance away, there should be an identical universe with a similar observable universe, just like our own, in which every particle in the universe is going to be repeated. So this assumption does require that the universe be infinitely large. If you want to read more on this, here's a nice article that talks about the notion of parallel universes. And this is one type of parallel universe, and all it requires is a infinitely large universe because eventually every possible arrangement of particles is going to be repeated.